Hello everyone, this is the video lecture for College Algebra Math 1414 Section 4.5 Applications. Basically just word problems. And there is nothing mathematically new, so we're just going to do it. A is equal to 969.1 e to the 0.016 t. I believe that this is a population problem, and it's funny because we just did one in the last section. T is years after 2003 this time, and it says when will the population be 1119? Sounds like a lot. So 1119 is equal to the 969.1 e to the 0.016 t. All right, solve for t. If you remember, there was a trick that I used. I called it the progression. And so it's ln of the 1119 over the 969.1, all divided by the 0.016. See the progression? And calculator. And I got 8.988 years. Of course, that's not what they're wanting, because we start with 2003. You add the 8.988 years, and I got 2012 is what we want. So there you go. Round to the nearest year. Wow, that was super easy. No math involved. Well, I mean, not really, but you get the idea is that if you know the style, the progression thing, it's super easy. Just like I said in the last lecture, all you're doing here is just filling in the three boxes with some numbers. Right there, there, and there. 1, 2, 3. 1, 2, 3. That's it. Very simple. Or you could do the divide, ln, divide. But again, I would say refer back to my last lecture for how to do that. 4, 5, 7. It says in the year 2000, we have a population of 5.99. That's a 5. But now in the year 2060, we're projected to have a population of 11. I'm guessing this is millions or something. And so they say use this formula. A is equal to A naught e to the kt. That's A is equal to A naught. A naught. Let me try to redo that one. Naught. It means initial. It's your initial population. This is your final population. K is your rate. T is your time. This time it's in years. And there you go. There's your formula. Go! Figure it out. I think what they're wanting here is... what are they wanting? Oh, they actually want the model. They want you to actually write this model as the answer to part A. Okay, well, let me tell you to start with here. This is your A naught. That's your initial population. It's what we're starting with. So that's super easy. To find this K, I need to find my T's and stuff. So notice right here, these guys, T would be what? 60. And this guy right here is going to be your final A, at least for right now. So then I have now 11 is equal to 5.99 e to the k times 60. You see the progression? You can use that for k or t. Always works. And look, you don't have to do a lot of math. Totally recommend it. I got 0.01013 for my rate. And so they say, now what's the model? What's your model? And so A is equal to, and then they have a box. Well, it's the 5.99 e to the k. I already got that. T. Now notice here, I only got 2 decimals because down here they say blah, 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 2 decimals. Something like that. Okay. So right there you go. 2 decimals. Never use just 2 decimals. 6 is safe. How many decimals should we really go out? 6 is safe. I'm just following their procedures here. They say 2 decimals, and I follow through. So that's part A. Part B is using this formula. It says, when will the population be 8 million? That's a question mark, though it doesn't really look like that very much. Question mark. It looks like a 2. Question mark. That's a little better. Okay, so I got 8 is equal to 5.99 e to the 0.01 t. I know that you have more decimals here, and in reality, you would use more decimals. But they don't want more decimals. They want you to use the answer from part A for part B. Okay. Do you see that progression? I'm laughing because it's like every single problem is the same here. There's nothing new. And that's okay. That's okay. It makes it easier on us, right? I got 28.935 years. Of course, as you know, we started in 2000. And so then we got 2029. Rounded, of course. Cool. I'm telling you guys, this is important. From here to here, you've skipped like 5 minutes of work. At least you've skipped about 3 solid steps, if not about 6 write down steps, like copying, write it down steps. And every time you copy something down or you write something down or try to do a step, you could get something wrong. I mean, it happens to me too. Every step there is another possibility of getting something wrong, missing a minus sign or who knows what. That's why I'm recommending this. It's just so easy to do. Just copy paste. It's not hard at all. Do that. Okay. It's good to know the divide, ln divide. We'll have to use it once in a while, I'm sure. But for now, oops, we got this. Okay. So they're talking about carbon-14 dating, and they got this formula for you. And they say how much carbon-14 is around after 5,243 years. Well, that sounds like a T to me. So you know what you're going to do, right? You got a T. What are you going to do? You're going to plug it in. That's it. That's the entire problem. You did it. Woohoo! 0, 0, 0, 1, 2, 1 times the 5, 2, 4, 3. Put this in your calculator. Scientific calculator, stuff like that. We got 8.484. And this is grams. Carbon-14 or whatever. Cool. That was easy. Next one. I did it not because it was hard, but because it's like, what do you do? Well, you just plug it in. So I do those kind of questions too. Half-life. When they talk about half-life, they have very specific understanding. So let's talk about half-life for a minute, and then I'll actually get to this problem. Half-life means that you had 100% of some, I don't know, radioactive material, and it's now going to 50%. Let's say volumetrically. The time that it takes for you to get from 100% to 50%, that time is the half-life. Okay? And then what's half of that? Would be 25%. And half of that is going to be 12.65, whatever. I don't know, 12.5%. You get the idea. But each one of these is another half-life. They're all the same. So let's say I had like an hour. So this would be 1 hour, 2 hours, 3 hours. You get the idea. It's always going to be consistently going down by half. And so now, this problem, particularly, he says that we got 32 grams initially, and then the half-life is 10 seconds. So that's pretty fast. And so then, here we go. It says, after 10 seconds, how much do we have gram-wise? Well, what's half of that? Because that's a half-life, right? So what's half of that? It's 16. Very good. So what's after 20 seconds? Again, that's now another half-life, so it's now at 8. And then what's after 30 seconds? And you get a 4, and then a 2, and then a 1, and then a half, or whatever it is. Blah, 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 blah. It's super easy. 4, 5, 19. This is a classic problem. 21% of this carbon-14 stuff is left over, they say. How old is it? So I got A is equal to A naught. Oh, that A does not look very good today. There we go. A is equal to A naught E to the, and they give you this formula 000121T. Okay, well, how much initial do we have? Well, they're assuming that we have 100%. So 1.0. 000121T. And so my final amount, that's 100%. They say we got 21%. There you go. Now it's 21, was 100. There you go. Solve for T. So, you know what I'm going to do here? I am going to do it the long way. Yep, I'm going to do it the long way for one time at all. So I'm going to say divide by 1.0. Oh my gosh, I got the same thing. You could do that progression that I've been doing every single time. That's what I have in my notes out, honestly. I'm going to ln both sides. The ln and the e are going to cancel. I'm just doing this because it's funny. And then I'm going to divide by that number, that decimal, that number. That's supposed to be a 2-1. Okay. Calculator, I got 12,897.915 years. Okay, awesome. So, I also did it for another reason. There's a formula kind of embedded here. Let me give you some formulas. When it comes to half-life, I just always forget the L there. When it comes to half-life, if you see half-life, there's some formulas that I always use. K is your rate. Let me write rate in English. Is equal to ln of 0.5 divided by the actual half-life. So why 0.5? Is it always 0.5? Yeah. It's 0.5 because it's half-life, half. What is 0.5? It's half. Okay, cool. So that's your K, that's your rate. T, some kind of time that it takes to decay into something or other, kind of like what we just found a second ago, is ln of some kind of a percentage divided by the K that you had just found. Doesn't this look familiar? Look, ln of a percentage divided by the rate. It's right there. So these two formulas are really cool. I'm not going to use K anymore, I don't think. That's cool and all. I'm going to use rate. But we already know it's K because, well, it's right there. So those two formulas, super important, super cool. They're super easy because they're already done for you. Let's use that on the next problem. So then I got 4, 5, 29. I got, well, they say to use this A equals A naught e to the KT, but I know better than that. We're going to use these formulas right here. So, anyways, I got half-life is equal to 26 years. And it says how long to decay to 84%. Step 1, my K, my rate, is equal to ln 0.5 divided by the half-life. Turn the page. Negative 0.0266595. I even have a note here on my paper. It says 6 is safe. I'm going to write it down. 6 is safe. Yes. How many decimal places did I go? 6. Here, I went 7, didn't I? Yeah, I did. Yeah. Well, I'm more than safe. Number 2. So step number 2, I want to find that time. It says how long, so I do it. So ln of the percentage, 0.84. Notice that I'm using decimal format, divided by the rate that I just found. And so I go to the calculator and I get 6.54 blah 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 blah. They round it to 6.5 years in my math lab. Okay. Well, you don't need to type years in my math lab. 6.5. There you go. Oh, actually, you do need to type years in my math lab. Ha! Let's talk about that. So this one has a blank and then another blank. And this is a drop-down kind of thing. I don't know, maybe a little arrow thing. You drop it down, and they got a big list of options, and years is one of them. Pick the years. Pick the years. And then, of course, you would put your 6.5 right there. I don't know why they would have anything else other than years here. That's all we're talking about. Don't put days. Don't put grams or something. Okay. 4, 5, 41. This is a pretty cool problem here. And this is a, hey, we got to do this the long method problem. What we're looking at is logistic growth model. This is called a logistic growth model. This is a little different than the other ones we've already done today. And this one, this problem in particular is talking about world population. Wow, that was terrible. There we go. World population. So we got this thing, world population. And they're just asking, when will the population of the world be 11 billion? Okay, so I mean, basically I just put an 11 out here, and then I start solving. So I mean, the math, it's going to take a couple minutes to do. The concept is very simple. I mean, here, I mean, if you want to just do it on your own, there, go. Solve for x. And that's fine. But I want to talk about logistic growth models for just a second, because it's actually really interesting. It's a little different than what we've been doing so far. Normally when they say growth or population growth or something like that, exponential growth, it just looks like this. This is exponential growth. Oops, growth. There you go. So basically it's just going up. Going up, 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 up. Over the long run, what does it look like? Well, it looks like that. Okay, cool. Well, so it looks like it's going really, really up. That's what exponential growth looks like. Well, what about logistic growth? What it does, it actually is growing, 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 and then it starts to slow down. And then it starts to flatten out. And so it actually flattens out to some kind of maximum up here. In this particular case, it's 12.57. It is the numerator. That's where it caps out. It's a maximum for it. And so something to think about, look right here for a minute. Just view right here. Doesn't it look like, oh man, it's growing? Like if that's all you ever looked at, wouldn't it look just like this? Exponential growth. And think about it right now, world population, all that, it seems like, oh man, exponential growth is getting like so much. Well, that's exactly when it's actually the turning point. You see, the turning point now is that it's going to start to slow down. And you're actually seeing that. I mean, I know this is, I don't want to date these, so it's like not too dated, but you can see around the world, different countries and different regions of the world where population's actually decreasing, actually. Europe, some parts of Asia, they're actually getting less than more. So you can already see the effects of us slowing down to a particular point. Okay. So now without that lesson, let's actually do the math. Back to what we're going to do here. I'm just saying, hey, this is applicable, and it's cool, It's cool to see these problems, work through them, and see that it actually makes sense in the real world too, So how do I solve this mathy-wise? What do I do? Well, you do a lot of steps. First off, this is a big fraction, and I do not like fractions, so I'm going to do that. I'm going to move it to the side. Now, I want to also move the 11 over, but I'm not going to do it just yet because I want to do each step individually right now. So this is times 11 equals to 12.57. Now I'll divide the 11. I just want to make sure that I don't skip any steps with you right here. I know that I do skip steps with you on a lot of problems. And if you haven't noticed, well, that's good. If you have noticed, well, I'm not really sorry. I know I need to be sorry, kind of, but you're going to move on to pre-cal. You're going to move on to calculus. That's why you're in this class. Eventually, we will be skipping steps. So it is good to, get the hang of it slowly. I try not to skip a lot of steps, honestly. I don't like skipping steps. Divide. There's a lot of steps to this one. That's okay. That's okay. That's why I'm slowly going through it. Now, couldn't I have, I don't know, simplified some of this stuff on this side by now? Yeah, let's go ahead and do that. So I'm going to put that whole thing into the calculator right now. So 12.57 divided by 11, enter, minus 1, enter, divide by 4.11, enter. And I got a 0.034726. Okay. Is equal to this thing. So let me rewrite that. I got a 0.26x is equal to 0.034726. It kind of looks a little weird to me. I sure hope I'm doing it right. No, yeah, that's correct. Yeah, I'm looking at my notes. Okay, yeah, we're good. So ln both sides. To cancel an e, you want to do an ln. Got to do it to both sides, of course. 2, 6, and they cancel. So remember how I was doing that progression? You can kind of use that at some point here on this problem. But obviously there's merit to doing it the long way sometimes too. Because, well, look at this problem. You had to do it at some point. So it's okay to do the quick version. It's also good to do the longer version. I guess it's kind of like synthetic division and long division. It's kind of good to do some, and then it's kind of good to do others. Regardless, I got 129.24 years. This problem actually started as X was years after 1983. So I'm going to add that, 1983, plus the 129.24. And you actually get 2112. That's a long ways out. If this recording's still around by that time, wow. Doubt that's gonna happen. So anyways, there's your answer. Cool. I think, and I just want to make sure you understand, they might ask another question, like what's the limiting size or something like that. I just want to make sure you really understand that we're talking the numerator of the original. Like I go way back right here. The numerator of the original is called the limiting size. The limiting size. And all that is, again, just capping on this, it's that maximum cap for the problem. I don't know what problem it's. It might be the other one that's similar to this, and it'll ask for limiting size. Just look at the numerator. You don't have to do anything else. It's very simple. Okay, I believe that's it. I have nothing else. So thank you very much, and have a great day.